So a very warm welcome to everybody tonight and to our distinguished speaker, Professor Jim Al-Khalili. Before we listen to Jim's talk, there are a few things I would like to say first. Health and safety. In the event of a fire or other emergency, then obviously we need to vacate the building, and either through the doors here behind where there's steps down to a door out into the alley and then the high street, or obviously the way you came in.
Is there any event of any blasphemy as well?
I'd like to thank everyone who is contributing to this evening. Trinity Centre staff for facilitating our use of the hall. Godalming sixth form students, Jonathan Holmes and Jessica Horn, for video recording our event. This will be put on YouTube, and you'll either be able to access it directly through YouTube or through the Farnham Humanists website, which is farnham-humanist.org.uk. We've also got Hannah Miles-Jewell and Anna Smith from Godalming Sixth Form College over there, and thank you to you two because they are producing a write-up of the evening to put out to local media. And I'd also, of course, like to thank our committee for all the hard work in getting the evening going, in particular Sue Shaw, our secretary, who's done so much for the evening, so thank you. 10 years ago, several of us here tonight received a letter from the British Humanist Association inviting us to a first meeting at Alec Leggett's house with a view to forming a new humanist group in Farnham. Since then, our growing group has hosted annual debates with eminent national speakers, raising over £3,000 for charity, debating motions on topics of ethical, moral and current interest. Motions such as we support a wholly elected House of Lords, morality without religion has no firm foundation, to ones relating to nuclear power, electoral reform, secular statehood, assisted dying and whether there can be a just war. This November's debate will be on state-funded faith schools. Over the last 10 years, we have locally represented non-religious views in the community, for example, providing, when requested, pastoral support in hospitals and hospices, speakers for schools, colleges, and most recently, the University of Surrey. We've also provided secular inputs to the religious education Surrey syllabus and also to local council equality groups. Many people know of the very personal and dignified non-religious funerals that humanists have conducted for many decades. As well as funerals, specially trained members of our group have also conducted ceremonies to celebrate marriages, civil partnerships, and also to welcome a new baby. Within our group, we've also had a lot of fun, socialising and exchanging ideas on a whole range of issues. And we're now looking to start a similar group in Guildford, so do let one of us know if you might be interested in that. We're also, as you may have seen from what's put on your seat, as chair, as it were, that we're running a couple of evening discussion workshops titled Exploring Life, a Non-Religious View. They are open to all beliefs, and we see them as fora for sharing and understanding different people's views on some of life's big questions. They are free, and there will be refreshments, including cake. So again, let us know if you might be interested in coming to one of those. Humanism is not a religion. Humanists are agnostics and atheists who think we can work out for ourselves what's right and wrong based on empathy and compassion. We believe we can find our own meaning and fulfillment for the one life that we know we have, and that the best way to understand the world is from evidence and science and using reason. This importance of science as the best method of inquiry, including about the universe and our place in it, brings us, of course, to what tonight is all about. We are very honoured to have Professor Jim Al-Khalili, OBE, here tonight helping us celebrate our 10th anniversary. Jim is a professor of theoretical physics and has the chair in the public engagement in science at the University of Surrey. He is an author of many popular science books. His latest, Paradox, The 9 Greatest Enigmas in Science, was published in 2012. He has hosted many BBC productions about science, most recently last October, Light and Dark, a 2-part series on BBC 4. He is often on Radio 4, and the latest series of his programme on famous contemporary scientists, called The Life Scientific, started again last week with Peter Higgs talking to Jim about the story of the Higgs boson. Jim has also broadcast and given many talks on Arabic science. Wikipedia says Jim has been a supporter of Leeds United Football Club since the 1970s. It also quotes Jim as saying that as the son of a Protestant Christian mother and a Shia Muslim father, I have nevertheless ended up without a religious bone in my body. Since January of last year, he has been president of the British Humanist Association, and I would now like to warmly welcome again Professor Jim Al-Khalili to give us his talk.
Thank you very much, Jenny, for that rather long and cringe-worthy introduction. Good evening, everyone. As I think was alluded to, tonight's lecture is really a science lecture. I could have given a talk about humanism. I could have told you about why I'm an atheist and various anecdotes and stories, and I'm sure you can ask me questions at the end if you like. But essentially, it seems in recent years that there's a coming together of various, science is becoming more popular and more embedded in popular culture in this country. There's sort of the secular movement is gaining in momentum. There's the skeptics movement. There's this drive and call for rationality, for evidence, and so on. A few months ago, sometime last year, I don't know if any of you remember, in the Sunday Times, a reviewer complained about how the BBC was being overrun. Sorry, Lord. If there ever was a sign, I may have got it wrong. Where was I? You know how you have this, I went through, as a teenager thinking, well, I pray really hard to God. Look, now is the time. If you exist, show me, do something. Just let me think. If that happens, I wouldn't be here this evening. article in the Sunday Times saying the BBC was being overrun by humanists, and it quoted people, science broadcasters, essentially me, Brian Cox, Alice Roberts, others like Robin Ince, Sundara Green, Adam Rutherford, with presenting lots of science documentaries on radio and TV, and we're all associated and connected in a number of different ways with the British Humanist Association. And my first reaction was, what a strange thing to say, to feel somehow so insecure that the BBC is being overrun by humanists. And in any case, let's wait until Thought for the Day is broken away from the mould where you have to be someone of faith before you can pronounce on and give sort of reasonable thoughts. But no, I'm not going to be talking about that. I want to talk about the issue of whether we have free will, and how we reconcile what that answer might be, whether we're happy about it. Now, I'm going to talk about this not from the perspective of a philosopher or a neuroscientist or a psychologist, but from a perspective of a physicist. Now, that may mean that some aspects of what I want to talk about may sound naive to people who spent their careers thinking about the nature of free will. But when it comes to the physics, I feel I'm on solid ground. So, yes, it's going to be a talk about science, and there's going to be aspects here that are a bit, if you don't have a science background, you'll have to stick with me, because some of them are rather mind-bending. I want to start by, first of all, ruling out certain naive assumptions and concepts that I would say are wrong. Wrong-headed arguments such as, not only is our fate determined, but it's literally determined by the stars and planets. It's still actually quite surprising, the number of people who look to the astrology charts in newspapers and magazines to determine what's going to come next. Our fate and all that happens in the universe is known to a higher power. So what we think to be free choices that we make are really just part of God's plan. Or that our fate is indeed in our own hands because we are more than just mechanical machines subject to the laws of physics. This is what's called the mind-body problem, that we have a soul, a spirit, something else beyond just the physicality of the atoms that make up our bodies. I would argue, to begin with, I want to dismiss those three arguments. Okay, I want to also, I don't know, can those at the back see some of these fonts? I hope they're not too small. Yeah, good. Not the bottom ones, right? Well, that's not my fault. I'll read out anything, anyway. So hopefully you won't miss it. So I want to define a few concepts because I'm going to refer to them and come back to them throughout the talk. First of all, what do I mean by determinism? This is what philosophers call causal determinism. It's the basic idea of cause and effect, that something happens because something caused it. Okay, that events in the past cause events in the future. So if you know the initial conditions, the state of everything now, then in principle you can predict what will come next. If you know everything about the details of the state of a system now, you can, provided you know enough physics or chemistry or biology or whatever it is the science that system is described by, you should be able to calculate, compute, work out how it will evolve in time, what events will come later. Randomness, now you know what a random number is, something that's just, that isn't determined by anything else. It's the opposite of determinism. This is where individual events cannot be determined precisely in advance, because they don't depend on past events, actions or conditions. In physics, we often refer to this as indeterminacy, that there isn't a cause and effect sequence of events. And then there's predictability. Now, if a process is deterministic, so if future events really do depend on past events, then in principle, we should be able to predict and calculate what will happen next. In principle, and that's going to be quite an important concept, that given enough information and enough knowledge and enough, a big enough computer, clear enough brain, provided we know everything that exists now, all the conditions now, we should, in principle, be able to predict what comes next, provided the process is deterministic. If it's indeterministic, it's random, then of course we can't. Doesn't matter how well we know the state of the universe now. Okay, those are the three definitions. Right. I would argue that there are four options available to us when we want to talk about the nature of free will, or whether free will exists in our universe. There may be more than four options, but that's because I haven't thought about this subject maybe deeply enough. I haven't spent enough of my life thinking about the nature of free will. Just waded in, as physicists tend to do. We can sort this out, don't worry. It's all very logical. Okay. Option one. Determinism is true. Our universe is deterministic. We are part of our universe. Right? So, all our actions, everything we do, could have been predicted in advance by whatever. Higher being, computer, someone else. If we live in a deterministic universe, all our actions are predicted, that means we have no free will. We think we have free will. We think we're making free choices, but in fact, since we are part of, embedded within a deterministic universe, every cause will have an effect in the future. Everything we do would have been caused by something else, not because we decided we wanted to do it. That's one option. The second option is that determinism is true, but nevertheless, despite that, somehow we can still have free will. The third option is determinism is false. We don't live in a deterministic universe. There is a built-in randomness to the universe, and that randomness gives us back free will. That because things aren't determined, the future is now open to us to make free choices. But option 4 is also that determinism is false, but we still don't have free will because events happen randomly. Then we have no more control over random events than we would if everything was predetermined. So it's they're sort of opposite, logically opposing views, both built on the fact that the universe is not deterministic. Okay, so determinism is true, so there's no free will. Determinism is true, but there is free will. Determinism is false, there is free will. Determinism is false, there isn't free will. 4 different concepts. Now I want to break away from philosophy, talk about physics, and talk about what we understand about the universe and its nature and our place in it, and then step back and say, what does that force upon us in terms of these 4 options? Before modern physics developed, so pre-20th century, we lived, or scientists believed that we inhabited a universe that was very deterministic, a clockwork universe. The universe of Newton and Galileo, that you could break down in principle to its smallest pieces, the cogs and wheels, the atoms, the particles, the forces between them, down to the fundamental building blocks, all of which behave according to the laws of physics. Whether or not we had discovered those laws is a different issue. But if they're all working according to simple, deterministic laws, if this object hits that, it'll bounce off in that direction at that speed. And it doesn't matter how complicated the system becomes, how many atoms are involved, it is still deterministic. There's no magic in there. It's a reductionist view. And even we humans, even our minds, our human consciousness, ultimately would be part of this clockwork universe, that everything is predetermined. Now, I'm not arguing whether that is right or wrong. I'm just saying there was a, this was the understanding by the end of the 19th century, certainly among many physicists and chemists, that we were reaching the limits of what we could understand about the universe. That it was just a matter of dotting the I's and crossing the T's, and we would have all the theories that we needed to describe everything. Not too dissimilar from the views of some physicists today, in the early 21st century, feeling we're coming to the, ultimate knowledge. We've discovered the Higgs boson, but what else is there? It's everything, all the pieces of the jigsaw are almost in place. But by the beginning of the 20th century, there was a revolution in physics. Albert Einstein, probably more than anyone else, helped change our perception of the nature of space and time. The title of one of his papers in 1905 on the electrodynamics of moving bodies, that was his first paper on his special theory of relativity. Now, Einstein in 1905 published a number of papers. Any one of them would have made him a household name, certainly within science. If not, then why he didn't. He didn't actually become a household name as a public figure until 10, 15 years later, after his general theory of relativity. So Einstein came up with mathematics that atoms really exist by explaining something called Brownian motion. He showed how light is also made up of lumps of energy, particles, atoms of light, called photons. But of course, what he's most famous for is his special theory of relativity, in which he said that space and time are not what they used to be. Space and time are not separate. They're not absolute. Until then, and that's probably still the way our common sense view of the universe is that space is the stage in which events happen. And time is external to it. Time ticks by independently of space. Einstein said no, time and space are mixed up together. You can no longer talk about three-dimensional space and one dimension of time. You have to talk about 4D space-time. And this led to the notion of the block universe. Admittedly, this wasn't originally Einstein's idea. It was something that came up, proposed by other physicists a few years later, but he certainly embraced it. Now, four-dimensional space-time is not something we can imagine. Our brains are three-dimensional. You can only think in 3 dimensions. Some people say, yes, I can imagine what a 4-dimensional object is like. Rubbish, you can't. Making it up. However, Einstein said, look, time is like another axis. It's like another direction. Now, we're familiar with 3 directions of space. I can walk forwards, backwards, side to side, jump up and down. These are 3 axes, all at right angles to each other. Try drawing another line that's right angles to all those 3, and it's impossible, because of course we live in 3-dimensional space. And yet Einstein said time is that 4th dimension. Time heads off in another direction, right angles to all the directions of space. Forget even trying to think about it. But the way we can imagine it is to throw away one of the dimensions of space. Imagine we don't live in this 3D world. Imagine we live in a 2-dimensional, flat, cardboard cutout world. But because you think in 3 dimensions, you can imagine, visualize that as a 3-dimensional block. What I've got here is space squashed to that one surface, that plane, which means that time is the axis that's now running along horizontally. Any slice, like a loaf of bread with a slice of loaf in the middle, that is all of space at a particular time, at a particular moment. So that's our universe now. A point in that, before that is the past, in front of that is future. This is our now. And our now, somehow, not something that anyone really understands, creeps along the time axis. A point in the now is a here and now. This is where I am at this moment. This notion of a block universe turns out to be very, very powerful a concept and helps us understand a lot of what Einstein was saying about the nature of space and time. But what it does is give us a universe that is even more deterministic and bleak and set than the Newtonian clockwork universe. In that lumpiness, that's what's called quantization of light, very soon evolved into a theory that was used to describe the structure of all matter. Developed by people like Niels Bohr, Danish physicist who came to Britain, worked with Ernest Rutherford during the First World War. Later, Niels Bohr went back to Copenhagen, set up his institute there, and gathered around him many of the greatest minds in physics at that time. Men like Werner Heisenberg and Wolfgang Pauli and the Englishman Paul Dirac. And they hammered together what we now call quantum mechanics. Now, quantum mechanics is a theory that doesn't talk about the nature of space and time, the nature of the entire universe. It's a theory that zooms in on the tiniest structures of matter, the building blocks of the universe, down at the level of molecules, atoms, and the particles that make up atoms. What is so revolutionary about quantum mechanics, and it's called mechanics because to distinguish it from what we call in physics classical mechanics or Newtonian mechanics, the forces and energy and momentum, the stuff that we learn at school. None of that applies down at the micro scale or the level of atoms. A different set of rules applies. And by different, I mean very, very different. Very counterintuitive, very strange, hard to grasp and understand and even believe. Niels Bohr, the father of quantum mechanics, famously said, if you're not astonished by quantum mechanics, then you haven't understood it. You are meant to be astonished. And most physicists, when they learn quantum mechanics, the way they code it is not that they understand how it all works. It's they say, they just accept it. Okay, that's how the universe is down at the scale of the very small, and it works. I will just use it. Now, quantum mechanics has turned out to be the most powerful theory in the whole of science. I have had this argument with biologists like Adam Rutherford, but I will say that quantum mechanics beats Darwinian evolution with one hand behind its back. Biologists don't like us to say that. Quantum mechanics has been proven for almost a century now to be an extremely powerful and accurate description of nature. Without quantum mechanics, we would not understand how electrons fit around atoms, how atoms fit together to make molecules. We wouldn't have modern chemistry without quantum mechanics. We wouldn't understand the structure of materials. We wouldn't have understood the nature of how objects conduct electricity. We would not have understood semiconductors. We wouldn't have developed the microchip, or the computer. Most of, people have worked out some ridiculous fraction of all, the GDP of a third of the GDP of the US is built on technology that wouldn't be possible without an understanding of quantum mechanics. It underpins most of modern physics and chemistry. But at its heart, it's very, very strange. And it's that strangeness that I want to focus on and try and link it in with, to see whether it has a connection with the nature of free will. You see, at a fundamental level, quantum mechanics says the universe is not deterministic. It's indeterministic. There's a built-in randomness that is not to do with our ignorance, but is a fundamental feature of nature. An individual atom that is unstable, that is radioactive, an atom of uranium or carbon-14, or an atom that will spit out an alpha particle or an electron and change into something else. We understand that process. We can work out half-lives. We can understand what it is that goes on. What are the nuclear reactions that go on inside an atomic nucleus? That's my day job, to calculate what is going on. But we can never predict in advance when a particular atom is going to decay, is going to spit out an alpha particle. Not because we don't know enough about it, but because nature, the atom itself, has not decided. It's just spat out an alpha particle without warning. It's a fundamental feature of the quantum world that events take place randomly. And only after, with many, many atoms, can we build up a statistical picture that gives us reliable numbers, like a half-life. A half-life is, if you have 1 trillion atoms of uranium, you can work out how long it takes for half of them to decay. And it turns out that time is the same as the time it takes for then the next half of what was left to decay, and so on. But individually, you cannot say in advance. This randomness, obviously, in quantum mechanics goes much deeper. And some of the features of quantum mechanics really are absolutely almost impossible to get your head around. Certainly the first time you hear it, you think, well, surely that can't be right. So I wanted to mess with your minds in case you hadn't come across what the American physicist Richard Feynman calls the central mystery of quantum mechanics, the two-slit experiment. Oh, there's some words there that I forgot. Nature hasn't decided what she will do next. This suggests our future is not predetermined. Ah, yes, exactly. Yeah, right, that's why I showed this picture. I talked about Einstein's block universe. The theory of relativity would suggest that the future is predetermined, everything is fixed, in a way that's much more extreme than Newton's clockwork universe. And therefore, there was no room for free will. Many scientists, including quantum physicists, have argued that quantum indeterminacy, this built-in randomness, at a fundamental level, gives us back our free will. They never go as far as explaining how or why, but simply that indeterminacy, good, at last, the future is not predetermined. It's open, it's free. Nature hasn't decided what it's going to do next, when an atom is going to decay. Magnify that up. That means the future, what's going to happen could be this or this, depending on when this atom decays. That freedom somehow gets, sort of translated into the notion that we could also have free will. The two-slit experiment. Okay, I'll whiz through this because it's all very straightforward. Imagine you have, and this is not quantum mechanics, this is just the nature of light. We know about light that behaves like waves. So imagine light being given off by a bulb. Now, of course, if there are any pedantic physicists in the audience, and I'm sure there are, I know that white light is made up of many different wavelengths, whereas really what we need for this experiment is something called monochromatic light, single wavelength of light. Let's assume that's what that is. Light comes off in waves with a certain wavelength and therefore a certain frequency, and it hits a screen with two slits. Each of those slits, as the light squeezes through, it then spreads out in a process called diffraction. So each slit is now like, if you were looking at it from this side, each slit looks like a new light source. And as the light waves radiate outwards, they will overlap. You'd have done this sort of experiments in a ripple tank water at school, possibly. I don't know whether they still do it at school now. Good, we still have ripple tanks. Excellent. Glad to hear it. But what you then get, when the waves overlap, you get something called interference. So where two crests of waves meet, they will amplify, and you get double the height of the wave. where the crest of one wave happens to coincide at a particular point and time with the trough of another wave, and if they're the same sort of amplitude, they will cancel out to nothing. And so this interference, if you then project onto a back screen, leads to what's called a diffraction pattern, which is a sequence of light and dark bands, here where the waves happen to have arrived in phase and amplified, and in between the dark patches where they arrive exactly out of phase and cancel. That's not quantum mechanics. That was known going back 200 years to a physicist by the name of Thomas Young in the early 19th century, who showed the wave nature of light. If I repeat the experiment now with particles, and I'm using here grains of sand. This is the same experiment, but I've sort of tipped it 90 degrees. Here's my two slits, and here's the equivalent of my screen. If you pour sand down on the two slits, each grain of sand will go through one slit or the other. Of course, some might just get trapped on top, but those that get through go one slit or the other. If you look back at the waves, each wavefront is spread out, and so it washes through both slits at the same time. That's the property of waves. But with particles, grains of sand in this case, each one goes through one slit or the other. So you end up, rather than having the, so this graph of this wavy line shows, you know, bright, dark, bright, dark, bright, dark. So that pattern of oscillations contrasts with a double bump, where either sand has gone through one slit or the other. That's not quantum mechanics either. Here's what happens when we look at the quantum world. First of all, we take a source of atoms, an atom gun that can fire atoms or any electrons, any subatomic particle. You can't see the atoms because they're very small. Got out of that one. Here we have two slits. Again, these slits, they will have a certain sort of thickness and separation that is appropriate for this particular experiment, but this is a very schematic diagram. Let's close the upper slit for a moment and only allow atoms to go through the bottom slit. Now there's a whole stream of atoms being sprayed at the screen, the middle screen with the slits in. So because a lot of them will just hit the screen and not get through. But some, let's assume, will go through the bottom slit. This back screen is coated with some fluorescent material that gives off a flash of light every time an atom hits somewhere. It deposits its energy and gives a flash of light. So you can see most of the atoms have gone through in a band corresponding to having gone through that slit. There's a few that have gone astray. We don't have to come up with a new theory to explain that. You can imagine these atoms are like tiny, tiny bullets or tiny balls or pellets. Some of them will bounce off the edges of the slit and that will deflect them above or below the main band where those that have gone cleanly through have arrived. The first quantum weirdness takes place when we repeat the experiment with both slits open. We don't get what we got with the grains of sand, which is what you might expect. These are like grains of sand, only much, much smaller, but presumably the same philosophy applies. You should expect to see a band there and a band there, but no. We see a pattern that looks remarkably like an interference pattern of waves. And yet, every one of these atoms was given off by the gun, and look, it's arrived here hitting a particular point. It's not like a wave. It's not like a wave washing through and hitting a large area of the screen at the back all at once. Each one of them is hitting it at a particular point. So how could they do what the waves do, of squeezing through and the waves spreading out and overlapping and crests and troughs interfering? Well, of course, if we didn't know any quantum mechanics, we could say, okay, maybe atoms are subject to certain rules whereby only a certain number of atoms could ever clump together in one place, and there are certain forces between the atoms. They bump into each other and say, me and my mates, we're going to go here. There's not enough room for you. You go somewhere else. And by the way, no one go in between. But there are a few naughty atoms that do. Logically, even if we didn't understand the details, you could find a common sense explanation. Let's check if that's right. Let's repeat the experiment, but send the atoms through one at a time. So you give enough time for an atom to hit the back screen. Of course, any given atom might hit the middle screen, fine, as long as there's enough time to allow it to have gone through one or other of the slits. Then you send the next atom through. So they can't communicate with each other, they can't knock each other and go in some coordinated way to create this pattern. Start off. And by the way, I should say, this is not, I know this is a nice schematic diagram, colourful pictures, this is not just a thought experiment. It's an experiment that's carried out routinely thousands of times in laboratories all around the world. We know this is what happens. Okay, it's not made up theoretical nonsense. So no, something I'm thinking about, theoretical physics. Have you ever seen in a lab? Well, I was in a lab today because we had an applicant day, and I'll take my students to show them around the lab and say, look, equipment. And I'll run back to my equations. So, we're sending atoms through, and what looks like a random pattern as they hit the back screen. But gradually, look what builds up. And again, you get the interference pattern. Each atom, when you think of what this means, each atom by itself is helping contribute its small part towards giving this overall interference pattern again. It looks as though these are waves interfering. And yet, we fired an atom individually from the gun, and we saw a spot appear here, an atom as a particle. It's behaving like a grain of sand, and yet somehow in the middle, it's doing something that suggests it's behaving like a spread out wave. In quantum mechanics, this is something we've grown familiar with, what's called wave-particle duality. But what does it mean? What is, how are these atoms getting through? Okay, so we can try and be a bit clever here. What if we were to spy on the atoms and we place, this is what we're going to do. Now place a detector above the top slit. The details are not so important, but this is something that will beep or flash if it detects an atom going through the top slit. And it won't. If a flash appears on the screen, a dot appears on the screen at the back to suggest that an atom's got through, without our detector firing, then it must have gone through the bottom slit. This is how we'll check. Do atoms really, when they come up to the two slits, suddenly spread out into clouds of atomness, into waves, and go through both? Or do they split in half and then recombine again? Or do they go through one slit or the other? Well, sure enough, half the atoms that hit the back screen trigger the detector. The other half of the atoms that hit the back screen don't trigger the detector. So atoms don't go through both slits at once, they go through one slit or the other. Thank goodness for that, they're sensible. But of course I've been rather crafty, I haven't shown you the results of the experiment. The interference patterns disappeared. The atoms are behaving like the grains of sand now. It seems that by looking at them, I force them to be sensible and go through one grain or the other, one slit or the other. There's one last bit of sneakiness we can try out. What if I were to switch off the detector? Well, I'll leave it there because, the atoms don't know, they're a bit stupid. I'm just going to go very quietly and unplug the detector so that I'm not recording where they go. I don't know, it won't beep or flash, so I won't know where that atom. But the atoms that are coming through, they don't know if it's on or off before they come through. Surely they can't be that clever. And I'll run the experiment again. And the interference pattern comes back. So, not only do atoms seem to know that, whether we're spying on them or not, they can do it without even seeing, they haven't even got to the two slits before they make up their minds what they're going to do. I've told it in a very anthropomorphic way, just to get across just how crazy and ridiculous the quantum world is. That's what really happens. It seems that the quantum world behaves in a different way depending on whether we're looking at it or not. Now, how do we cope with this? How do we figure out what it means? Well, the standard way of describing this was put together by people like Niels Bohr, Heisenberg and Pauli while working in their institute in Copenhagen. It became known as the Copenhagen interpretation of quantum mechanics. Quantum mechanics required, the mathematics was beautiful, it made beautifully accurate predictions about the properties of atoms and molecules and chemical reactions and properties of materials, and yet what was going on at a fundamental level, how an atom gets through somehow both slits at once to give an interference pattern when you're not looking, but doesn't when you are, that seemed to require an interpretation of the theory. The Copenhagen interpretation could be distilled down to the following statement. Shut up and calculate. Never you mind. If you're going to worry about what that atom does between the two slits, go and do philosophy, mate. You know, this is physics. And this is how physicists for generations have dealt with the mystery of quantum mechanics. By accepting it, saying what right do we have to, you know, describe the way the subatomic world behaves in common sense language that we are familiar with in the everyday world. That's what happens, get on with it. Of course, not everyone's happy with that explanation, and you might argue quite rightly so. Mathematically, we know what to do. We don't describe the atom as a particle. When we're not looking, we describe the atom as a presence, as the potential of atomness, the probability of an atom being in a certain place. So you could imagine it's a mathematical abstract notion, something called the wave function. And it's just a set of numbers that you can write on a piece of paper or generated by a computer program. But essentially what it gives you is the probability of finding an atom somewhere if you were to look there. It can't say where it is if you're not looking. It just says if you were to look, that's where you'll find it. So it says here, at this moment, this is a snapshot in time of an atom being fired from the gun. It's most likely to be found there, less likely there, and so on. It's like sort of contour diagrams. And as you evolve in time, that wave, that probability distribution, spreads out, behaves like a wave, and it squeezes through. What does it mean for probability to squeeze through? You know, this is not real, this is maths. But I can say I do the maths, and then what's the chances of the atom being, well, this suggests there's a 50-50 chance of finding an atom there or there, were I to look. And then there's those waves of probability interfere with each other until they reach the screen, and you can see there's a high probability of it being found here, 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 or here, no chance of it being found there, 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 or there. So the maths in dealing with this probability, indeterminism, randomness, is exactly what we need to describe the subatomic world, whether we like it or not. A number of physicists have tried to come up with different ways of interpreting what's going on in the quantum world. There's something like half a dozen standard interpretations of quantum mechanics that all fit the maths, but we don't know which one of them is correct, if indeed one of them is correct. So the standard one is the Copenhagen interpretation, which isn't really an interpretation. It just says you can never understand what's going on. Don't lose any sleep over it. But there are other interpretations. So people like Stephen Hawking and a number of cosmologists argue the best way to explain what's going on is to hypothesize that there are many universes. Ah, easy. That's all right. As a British physicist now living in America, Paul Davies, once said, This many worlds interpretation of quantum mechanics is very cheap on assumptions, but very expensive on universes. Some people feel, well, it's a big price to pay. But it just goes to show how strange quantum mechanics is, that physicists are prepared to propose preposterous notions that are really not much different from religious faith. Something that we have no evidence for, basically. Because it helps explain some aspects of the physical world. And quantum mechanics isn't constrained to the world of the very small. This image, this picture of the patchy-looking egg, some of you may recognize. This is an image of the entire visible universe. It doesn't look like it is. Where's all this? These are not stars in galaxies. These are different temperature patches of deep space. When you look out in space, one of the predictions of the Big Bang Theory is that the universe today, deep space, will be at a particular temperature, because since the Big Bang the universe has been cooling down, and about now it should be 2.7 degrees above absolute zero. You know, minus 270 centigrade. And sure enough, that turns out to be exactly what the temperature is. That's one of the big pieces of evidence for the Big Bang. But it also suggests that if when the universe was very small just after the Big Bang, it was subject to the rules of quantum mechanics, because it was part of the domain of the very small. And that randomness, that indeterminacy, that fuzziness of the quantum world got expanded out and got frozen in the structure of the universe as it grew very large. And you still see that today. You see fluctuations, differences in temperature. Not much. These are tiny, tiny changes in temperature between different parts of the universe, which are down to, it's an imprint of the quantum behavior of the universe when it was very, very small. Quantum mechanics, of course, another example of where quantum mechanics is seen around us, is in the re-explaining why the sun shines. Our sun shines because it's converting hydrogen into helium through a process of thermonuclear fusion. It's forcing hydrogen atoms, or more correctly, the nuclei of hydrogen atoms together in a process that eventually leads to the creation of helium atoms, the next element in the periodic table. And that process gives off a lot of energy. You hear in the news about the holy grail of energy that we want to create on Earth is fusion energy, and it's always 30 or 40 years in the future. But we understand the physics, it's the technology that we can't get. We can't create the conditions of the sun in a controlled way in a reactor on Earth. The way the sun pushes two hydrogen nuclei together is subject entirely to the rules of quantum mechanics, because essentially they are carrying out a process called quantum tunneling. They're doing the equivalent of me running towards a brick wall, disappearing and reappearing on the other side by magic. And I will not be demonstrating that. I'm not a quantum object. But that's one of the weirder aspects of quantum mechanics, and it's the reason why the sun shines, and therefore the reason why we're here. So there's a lot of mileage to quantum mechanics, and yet, at its heart, it says nature, the universe, is indeterministic. I would argue, let me just, before I show you those two French gentlemen, I would argue, however, I might as well say it now, I do not think that quantum indeterminacy has a bearing on the larger scale determinism of our universe. You see, apart from concepts like quantum tunneling of atoms in the sun, those are processes that take, nevertheless, although cumulatively they provide the sun with all the energy, individually it's down to individual quantum processes, two protons trying to punch through their repulsive electrostatic force that's keeping them apart. Once you get many trillions of atoms together, the weirder aspects of quantum mechanics, like the two-slit experiment, washes away. We don't see this quantum behavior in the everyday world. Those grains of sand would never behave quantum mechanically. You'd never get that interference pattern with the grains of sand. Why? Because they're made up of so many atoms that the weird wavy nature, the fuzziness of individual quantum entities gets all washed out and averaged out, and you lose it. You don't see quantum indeterminacy in the big, everyday classical world. So I argue that quantum indeterminacy does not rescue us from the deterministic universe that Einstein and Newton before him said we live in. But I do want to say something about what we have, about free will and what we can, how it sits within a deterministic universe. Two Frenchmen, Laplace and Poincaré, between them contributed a lot to our understanding of how we can predict, if the universe is deterministic, how you can predict what will happen next. Now, Laplace was given the task of calculating, it was the King of Sweden had proposed, had offered a prize of several thousand kroner to any mathematician who could prove beyond doubt that the Earth would continue to orbit in a stable orbit around the Sun forever and the Moon around the Earth. For some reason, the King of Sweden at some point in the 19th century got worried that the law of gravity would somehow change, or that the Earth system, solar system was not stable. Laplace took on that challenge. He didn't prove what the king wanted, but he did win the prize by proving something rather remarkable. That even a system of three bodies, in his case he looked at the Sun, the Earth and the Moon, you could not predict in advance indefinitely how it would evolve. Not if they're going around in exactly perfectly stable orbits, but any three bodies, three balls hitting each other. You could never get an exact solution. It's called the three-body problem. Poincaré took on this work after him, and it really led on to a field of study that flourished by the mid-20th century. It was the notion that, I mean, if we think of an example of a pool table, and you hit the cue ball on the pack of balls in the triangle, and you scatter them. Now imagine being faced with the challenge of repeating that exact same shot again. Obviously no one is that good at pool, but imagine in principle that you could hit the cue ball with exactly the same force, exactly the same point on the cue ball, and to hit one of those balls in the pack at exactly the right angle and strength. Surely you'd think you'd be able to create the same scatter. In principle, yes. But in practice, you'd never be able to do that. Because eventually, there will be some tiny condition on the table that will differ from those 2 points. Maybe the slight change of humidity, a slight grain of dust, or the way that the table is laying, or you would have to know the precise positions of every ball to infinite accuracy in order to predict how they would evolve indefinitely in the future.